Before we can really talk about the computer that's going to make up the bulk of this video, we need to talk about the company that manufactured that computer, but also the man who founded the company itself. And to really explain that, we need to go back to the 1960s. Fairchild Semiconductors was quite well established in Silicon Valley, but they were also in complete disarray. Employees and engineers were leaving left and right because of all sorts of internal squabbling, disputes, and other egos that were clashing against each other. Robert Noyce, for example, would leave and he would go co-found Intel. Lee Boycell was another person who would leave to go found his own company. Before he left, he was working with a team on developing four-phase logic. I don't know exactly how he was able to get that technology out of Fairchild and develop a company around it, but he did, and he didn't get sued, or at least not that I can tell he got sued. Surprisingly, the name of his company was Four Phase Systems. It was founded in 1969, and in fairly short order, they had established their own microprocessor and they were shipping a computer. Now, in 1971, Intel would also ship their own microprocessor. This thing right here. This is the Intel 4004. It's about 2,000 or more transistors. It's a very simple microprocessor. But this is where they started off. By 1972, the 4004 was kind of obsolete, replaced by this little chip here, the 8008. At the same time here, there were other companies that were developing their own microprocessors. I'm going to ignore IBM here because obviously they had their own engineering, chip fabs, and all that jazz going on. And we had Texas Instruments, for example, with the TMX 1795. That wasn't really a commercially selling CPU, but we're going to get back to that. Anyways, Four Phase would go to bundle their own microprocessor, the AL1. And this is an example of it right here. This is the CPU board. And in fact, this here has 3 AL1 microprocessors on it. This is using what's called bit slice logic, in that you can increase the bit width of a system by running multiple bit slice processors in the same machine. So this is actually, each one is based on an 8-bit bus. So you can go 8, 16, 24. So the computers that Four Phase sold were in fact 24-bit machines. It's weird, I know, I don't know the full logic behind it, but the point is, you've never heard of Four Phase Systems. You look kind of confused and perplexed, and you've probably never seen these machines either. Like, did they last long? Well, it's interesting. What happened is that in the beginning of the 1970s, they had enough clients that you could count them with one hand. By 1973, they had several hundred machines in the field, and by 1979, the end of the 80s, Four Phase Systems had consistently beat their own profit projections, and for 1979 alone had made over $178 million in revenue. They were a big and very successful company. And yet, for reasons I will explain, they disappeared by the 1980s. Also happening in this period of the early 1970s was a lot of disclosure, a lot of discussion. These newly discovered and newly available semiconductor microprocessors were really interesting, but there was no internet, and there was limited written publications that could be used to distribute information about it. So a number of individuals, Intel was involved in it, Four Phase was involved in it, Fairchild was involved in it. They would distribute white papers about the products that they had designed and scientifically how it worked and how you could adapt this into your own applications. And, well, obviously the ultimate goal here was to say, we have designed these fantastic chips here. Now we want you to develop products that use this. And this always was kind of a weird issue involving copyright and intellectual property, because when you're just kind of throwing things out there, as we've seen with more modern times, sometimes people will argue who will say who was the first for what. Texas Instruments was one of those companies that liked to keep full control over their products, the 7400 Logic series, for example. This would come back in the 1990s, late 1980s, and into the early 1990s with Texas Instruments, when they were realizing, you know what? For many years, we allowed other vendors and other fabricators and other foundries to manufacture and sell products that really we designed first. So they began a very long and litigious period which is well known in the industry as Texas Instruments versus everyone. That's right, the boys from Texas were looking to get every cent they could out of anyone who was using anything they dared to try and say Texas Instruments did not make. Among the many countless lawsuits that took place, Texas Instruments went after Intel and said, yeah, you remember that 4004 thing going on here? Did you know that we were developing a microprocessor before you ever had anything done? And Intel was like, most certainly not. We had this done before you did. The 1795 came out after the 4004. Maybe you're thinking about the 8008. But they went to court anyways. I don't have a lot of documentation regarding what happened during these court hearings and exactly what was going on internally, but I have to assume, and I'm just going to have to speculate, be facetious, and kind of dramatize this a bit, is that one night Intel's legal team was sitting around the kitchen table eating Chinese food, mumbling about the various cases that they were all having to deal with, and someone brought up, we have to hurry up with this whole TI versus Intel microprocessor ordeal, or otherwise they're going to bury us. Well, I don't have any other ideas on this one here. They seem to have us nailed saying that they were the ones who did it. Can we prove otherwise? Well, we can't prove otherwise because we have evidence out there to show we aren't the first. We win this one, we're liars. We lose this one, Texas Instruments gets rights that we don't have, or they don't have control over. Is there anything else we can work with? And then someone pointed out, remember Lee, he had that microprocessor. Oh yeah, the AL1, I remember that. What year did that come out? I think it was the 1960s or something like that. Have we tried bringing that out to Texas Instruments? What'd they think about that? Yeah, no, we talked about it. They rejected that offer, though. They didn't say it was anything good. Anything good? Can you explain more on that one there? Well, I mean, it's not enough to really consider it being a single-chip microprocessor. It was never used in anything really considered an actual computer. Now, telepathically speaking, I bet you that Lee Boysil was sitting in his chair watching TV when he heard and felt the disturbance in the universe of someone talking smack about his chip design. And as a result, he telepathically fought back on Intel's legal team saying, you will call me and you will have me make something to demonstrate just how much someone regrets ever mocking my architecture and design. And what happened is that Intel did contact Lee saying, can you demonstrate the AL1 can perform as a microprocessor and perform computational tasks as a computer in a courtroom? And Lee said, sure, I'll set something up and I'll make it working. And a week before this whole thing was supposed to go to court, Lee came in with this most amazing, most audacious demonstration I have ever seen. It was a clear acrylic box and it had 3 Super Nintendo cartridges on it. They had been gutted and restuffed with RAM, ROM, and I/O logic to drive a VT100 serial terminal. And at the very front of this demonstration was Lee's own specimen AL1 chip from 1969, years before Texas Instruments, years before Intel. So Intel could wash their hands and say, not us. And they demonstrated it running applications or code that was both prevalent and functioning on the Texas Instruments example and Intel's own example. Ultimately, what happened is that Texas Instruments would back off and they would never touch this again because ultimately they had just been torpedoed. There was no way they could challenge against this. And it's interesting, to this day, when you look up the 4004, even on Intel's own website, this was the first commercially available microprocessor. It was not the first, period. That would ultimately go to the AL1. But even then, it's not without its criticisms. You see, what Lee did in the background is a lot of abuse of the logic that he had available to him and to impress the courts and the lawyers to say, no, see, it's working. You see, the AL in AL1 stands for arithmetic logic. The AL1 is really just an ALU. It really does lack a lot of the components needed to make a microprocessor work in modern contextual terms. And yet he was able to pull that off using what was in the RAM and ROM in the other parts of his example, and Texas Instruments bought it, and they backed off. So I will leave that open to criticism there, that maybe this isn't the world's first single chip microprocessor, because it's missing a lot. But the fact that he was able to BS himself through that, I commend him. You did a very good job. It's also worth pointing out here, there's a much longer document that I'm going to recommend to you, and I'm going to link it down in the description below. Ken Schriff actually has a giant write-up on this and explains exactly why the AL1 is not the world's first microprocessor. So read that up first as well. Now that we've talked about Lee, let's talk a little bit more about what 4-Phase Systems was. They were a computer company in the early 1970s. Their primary objectives was to serve distributed data processing. At this time here, with the introduction of semiconductors, you could now make smaller computers. You didn't need a mainframe. When you had companies like IBM trying to sell you systems like the System 3, which was a huge computational device that was single user, could you do a little bit better than that? 4-Phase had developed a computer that could handle distributed data processing. That is, it could do word processing, it could do batch job production, and it could handle it all off to an IBM mainframe who would then do all the work for you. But the other major market that 4-Phase had is that they could configure machines as terminal emulators for IBM systems. Now, IBM could sell you a terminal system like the 2260 for a considerable chunk of money. Like, you got yourself the data channel option for your IBM, you then got the terminal controller, and then you would have one terminal, which used delay line memory. 4-Phase, on the other hand, could supply you, for the cost of that, a computer with the ability to support up to 32 terminals, emulating IBM's old system, with local storage and card processing options, as well as a number of other features and disk options that were available at the same time. And I'm sure IBM was absolutely furious that they were being undercut so badly, but they never really challenged 4-Phase on that one there. Ultimately, they would just try and build smaller systems themselves. These smaller systems also existed before the microcomputer revolution. I mean, 1971, 1974, you had like the Kenback 1, the Apple I was still several years away, the Apple II was even further away. The Altair 8800 was showing up in its infancy in the most basic of configurations around that time. Business computers would come out a little bit later with the rise of CP/M and NP/M and other similar interactive office operating systems. 4-Phase, on the other hand, would have their own thing, their own operating system, their own disk system. It was using the very interesting Diablo Type 30 disk packs that you would see on the Xerox Alto, which is funny to say that 4-Phase machines were available on the market years before the Alto. This is how far back this computer was. It is such a strange machine. Now, with all the money that 4-Phase was making off of system sales and software support, they obviously wanted to make themselves a large, lavish headquarters, and that they did in the core of Silicon Valley. Cupertino, California, North De Anza Boulevard, right off of the interstate. It was an enormous, sprawling complex surrounded by parking. This was their main administration and billing. It was their primary computing center. It was their engineering and R&D facilities. It was their chip fabrication and system assembly. It was their testing and rework facilities. And finally, it was their warehousing and shipping facilities, all underneath one roof. They also built an extended office building just off to the side later on, but they were doing really good for themselves. You could get yourself a benefits plan. You could also really well respect that Lee wanted to make a company that everybody enjoyed. And from the various 4-Phase alumni that I've spoken to, Lee was a heavily respected man. Like, everyone was satisfied with what 4-Phase was delivering, and everyone was proud of their work. And I have one system and a number of components, and that's what I want to talk to you about today. Now, forewarning, I want to point out that when I got this machine, it's rough. The previous owner before me received this from someone who had found this stored in its rack, upside down, in an open pole barn. Some of the boards were scattered around. We were able to scavenge together most of the components of this machine. The weather really did a number on some parts, so they weren't salvageable at all. Ultimately, this machine was supposed to be given to the Living Computer Museum. But when COVID came around and it closed, it needed to find a new home, and ultimately it came up available for free So I drove down to Washington State, picked it up and brought it back and did cleaning from here. There's a lot more work I had to do. We'll discuss that later. But let's start with the CPU itself. Now, the first time that you see a 4-phase computer, it's not going to be like a mini computer that you expect from the 1970s. IBM had their nice industrial look. Companies such as Data General or the Digital Equipment Corporation had very colorful, bright, vivid machines. This here is the front panel off of a Data General Eclipse, in fact. 4-phase was nothing like that, strictly business. Strictly 1970s. This is very, very, very brown. Not only is it very brown, it has gold highlights on all of the lettering on here. And in fact, the entire system here, the cast aluminum on the side, the aluminum paneling that's also here, is all aluminum. And it's some weird gold finish. I'm not sure what it is. This is all cast aluminum on the front here. The whole front here is just aluminum. It's a giant mass. This here is plastic, but that's a front panel for you. So where do we start off on the front of this machine? Well, first off, 2 key locks. The first one here is our main power switch. Yes, I do have keys for this system. The one next to it is the console lock. So when that's turned to the lock position, the console and label light turns off and the entire front panel stops working. There is all 24 switches for the 24 bits that are available within the system. They are also controllable as alternate functions and features using another 3 toggle switches up here. You also have your standard front panel controls. Load, step, system reset, a boot switch, and if you wish not to boot automatically, you can switch this to a manual mode, and then you can try using that and toggle something in. But otherwise, you're not expected to be using the front panel in this thing. Once the system is up and running through its other primary boot mediums, being tape, disk, or even punch card decks, remember that documentation card reader I had from many years ago? Yeah, this supports that. Well, once you get it loaded into there, you then discover that the 4-phase systems, well, they all use semiconductor memory. Not a single 4-phase machine was using core memory, unlike its counterparts in the industry. And that is because 4-phase, according to their own brochures and literature, were the first companies using solid-state computers. No core, anywhere. Even in the peripherals, it was all their own semiconductor design. Now, inside of here is more of 4-phase's work. The actual computer itself is divided into one large card cage here, but you also have different sections doing different features within the computer. The back section right here is all for the console. Now this is for distribution of video and control signals. It also uses these strange little jumpers, these things right here, to configure how each terminal operates within the machine. There's more jumpers here and there's cabling that would link it to the main system bus. Underneath this is the giant ferroresonant power supply. It's a linear, which powers the entire system. The card cage is also broken up into memory, terminal control, CPU logic, peripheral expansion. And then of course we have the front panel right here. Now I am going to try, I have this currently balanced on a piece of wood because I don't want to beat the crap out of the table. I'm going to try and slide this around, and I'm going to pull out some boards, or actually we're going to pull out all the boards, and I'm going to talk more about them. The first thing we're going to start with here is the memory itself. Now, like I mentioned before, 4-phase was developing their own semiconductors, so all of the RAM in this machine belongs to them. Yes, I am unfortunately missing 2 here, and that's a little bit of a problem. You see, because 4-phase was developing all their own semiconductors for their own computers, this is also the reason why the AL1 was not the world's first commercially available microprocessor. They built it, but only for themselves. And as a result, data sheets for every IC that you're going to see in this video here, that is white ceramic with a gold cap and the 4-phase logo, there's nothing that exists on the internet. Not a single piece of information. And why should there be? You weren't supposed to buy these components. This was all internal to 4-phase, and that I can tell, it's never gotten out. So I can't necessarily say what this is supposed to be substituting. It's going to be more than likely static RAM that we're looking at here. but I can't tell if these are 2 kilobyte or 1 kilobyte chips, or if there's something in between, like, I don't know, like 512 bytes or something like that. The system can hold 8 of these boards. Each board contains 48 chips. There is some conflicting information whether or not these are 48 or 96 kilobyte boards. I don't know if that's 96 kilobytes per board, 96 kilobytes in 1-bit increments. I'm not entirely sure at all, but these boards are absolutely beautiful. You may also notice there's these white rails that are running along here. So what 4Phase had to do, because these boards were so busy and they're only 2-layer circuit boards, is that there is your voltage rails and your grounds. They're running vertically along the top here. That is a method that other people use. This isn't completely out of the ordinary, but from what I've been told at engineers at 4Phase, they didn't like it, because if you ever had these pinched, you could short between the rails and it caused all sorts of stupidity. And then also you could end up like you probably see right here, where this is loose, it can break loose and you may not even notice it. So that section there needs to be addressed and probably repaired. I'm going to now drop that board back into the system carefully. And then we go another memory board, another memory board, another memory board. And then I have 2 open spaces here marked CG3 and CG2. I'll talk about those in a moment. But in front of that is our next 4Phase proprietary board. If I can get that out of here. The jumper is in the way. Move that there. This is the DT board. The DT board, or distribution and timing board, is, from what I can tell, a combination of memory management unit, but also the terminal controller. You see, 4Phase was doing a little bit of a secret thing here. And that is, instead of having something like a serial terminal where you could actually have image retention of whatever's on the screen, or block mode information like you might find with IBM 3270 systems, the system memory is also the video memory for not just one terminal, but up to 32 terminals at a time. So it needs some way to partition up the memory for each of those displays, plus the system, whatever applications, data sets, or utilities are running, and the core operating system itself all have to be managed and shuffled around in memory without ever colliding. And when one terminal calls for a screen refresh, this board that I can tell has to handle that. And it does so with this large 4Phase chip right here. Now there is a lot of bus driver and receivers around here, lots of transistors, lots of 74 series logic and diodes. There is another couple fun things here, like they have these jumpers that are being used to configure various assignments within the machine, and the reason you have to configure them are those 2 empty slots that I was talking about. So on the next 2 adjoining slots, I have these weird blue connectors, these things right here. So what these are edge connectors which run back up to the console distribution board that I mentioned sits right on top of the power supply. This here is a character generator board. So let me pull that out. This board here, again, 4Phase logic, but also it's kind of a blank page. And that's because this is the more low-end, more generic model. So this does character generation for up to 8 terminals. Hence why there's 4 boards, 8, 16, 24, 32. This system with only 2 character generator boards can only handle 16 terminals at one time. This is called normal intensity, which is to say that when you type or display something on the screen, it only shows one brightness of the text. With the enhanced intensity board, which looks a little bit different and has more chips on it, that there allows for 2 different brightnesses of your text. There's no other graphics that were available on the 4Phase machine, and it had to be all handled by these individual boards. So I'm now going to go and put that one in there. And like I said, there was 2 of these here. So let's take this jumper, and I'm just going to pop that back on top of it. I have 4 more memory boards that are living right here. And then we have an empty slot right here, and I'm going to explain that one in a moment. The next one here is the CPU board. Now before I talk about the CPU board that's in here right now, let's look at the actual AL1 board itself. And I have that sitting right here. So like I showed early on, here's the 3 AL1 bit slice microprocessors sitting right here. These 3 chips are marked RL, or random logic, so additional gates and things that are having to make up for the fact that these are arithmetic logic units. And then hiding over here are 3 ROM chips. And again, this is all 4-phase stuff. Good luck finding pinouts for any of this. These 2 unpopulated sockets right here are for a numerical option that I don't have. Also, like we saw with the character generator boards, this has an edge connector at the top. That's not used for anything on the CPU board. Instead, it's for debugging. The same goes with all the memory boards. They have little tiny headers on the top here for showing as a ground reference, a voltage reference, and the 4 clock phases are available right here, so you can do testing without having to use a board extender. Though, if you want to dig deeper into this, you probably do need a board extender. This system is not equipped with an AL1, even though it is a Model 470 machine, and you can't differentiate that between a 450 or a 430 because they all look the same. This one here has a completely different CPU board altogether, and it's not a CPU board. This is simply a CPU expander board. Again, it's using all standard off-the-shelf parts and components, and a lot of these very early LEDs are scattered around here. So this is for a CPU expansion called the 490, which adds a different CPU in bit slice, mind you, which accelerates the 4-phase system, both software and the hardware. And this machine has been upgraded to one of those. So I'm going to drop that back in there for the moment. And then I have 2 more slots that are empty right here, and these are the I/O interface boards. They're not in there again. I'm going to explain it to you now. So when I received this machine, I was missing those 3 boards. No memory parity, no I/O interface. So memory can't talk to the CPU. CPU can't talk to the I/O peripherals. CPU can't talk to the front panel. Nothing can talk to the consoles or controls. Without those 3 boards, this machine is unfortunately dead. So I'm not going to be able to demonstrate you to this machine, and that's why I'm going to focus more on just showing you the hardware, because really that's all that's left at the moment. But now we're going to move into the I/O and expansion bus. Now this isn't a fully expanded system, but it's pretty damn close. The first board I'm going to pull out of here actually looks kind of barren and empty. And what this is called is the 470 driver receiver board. This simply takes the 4-phase bus and converts it over for what is called the NP80 peripheral expansion cabinet. This is also a very good time to point out that you see this edge connector here? Looks an awful lot like S100. But if I reach over here and I go and reach for an actual S100 board, we can see this is not an S100 slot that the 4-phase uses. Instead, it's a little bit longer and the pins are physically larger. So you can't put S100 machines into this cabinet at all. But anyways, not much else has happened on here besides I've recapped it. We did a video on this quite a while ago, and also you may notice that this has shinier legs than any other component on here. And that's because I've already been doing some debugging and testing on this thing. So we're going to drop that back in there, and we're going to talk about the NP80 later. The next board that's hiding in here, however, is pretty much just an expansion cabinet for the I/O bus. This one here, little bit more logic, a lot more buffering and bus driving going on, much more high density connector at the very top here. It's strange, when we got the machine out of the pole barn, like this was here, the cable for this was here, but we were missing the actual expansion cabinet. The only thing I really haven't shown you is the power distribution unit, but it's a power bar, so there's really not much to show you here anyways. Much like with everything else I've mentioned here before, this is just 74 logic all the way across the board. Very early stuff. But this has been upgraded at least at one point in its past. Some of these have rather newer date codes. Is that 1985-03? So that's very, very late. So this has been upgraded at least once before, but it still has the 4-phase logo. I'm going to drop that back in here. Now I mentioned before that 4-phase could sell you peripherals with the machine beyond just disk and punch card. So this here is one portion of the tape controller that you would get. So it's two boards, lists itself as the 1600 PE Mag 2 and 1600 Mag Tape 1. And, well, it's got a lot more of these weird vertically standing rails on top. And again, it's just large amounts of 7400 logic. That's just the way it was. VLSI semiconductor technology, sure, was very proprietary at the time. Hence, 4-Phase was designing their own chips, but universally speaking, there wasn't yet a whole hell of a lot on the market you could use. So you just had to make do with intersil programmable logic and 7400 logic, to which, as we've seen, all of these boards have absolutely astonishing amounts here. This here also has two connections that would then snake off to the connections for not the tape drive, but the tape formatter. So I'm just going to loosely drop these back in here again. Can I put that in there again? There we go. That drops in there. I'm going to drop that one in there. And now we get into our incomplete board sets, where I'm pretty sure I'm missing something. So this next one here, from what I've been told, is a disk controller. What kind of disk controller? It's going to be a pack drive or a removable cartridge type disk controller. This calls itself the 8437 Control 1. It actually has its own RAM hiding over here, and this is all 1979 dated stuff, and a CPU which is kind of faded. It's difficult to actually see what that is. So what is that? SY6512A. Pretty sure that's a CPU. We're going to say it's a CPU. If not, I'm going to correct myself over here. Then we have some intersil programmable logic over here that's got its own little part numbers stamped onto it. But remember how I was saying there, that's kind of a faded masking on that chip, right? Well, then we get to the last card that's in the system here, and this is the line printer output card. And then immediately, uh-oh, something's going wrong here. Usually you would associate this kind of damage with overheating components. This is just being exposed to the ravages of the Pacific Northwest. This whole side of the board here is green. This section over here has turned brown. And that's either from UV exposure damage, sunlight damage, or some sort of weather damage from facing out towards under a stack of boards that were sitting on top of it. But otherwise, that makes up now the bulk of the system. I really wish I could demonstrate this thing to you, but I can't. Like, if I were to plug this thing in right now, like, you'll get fans, you'll get the whole front panel lighting up, and by the way, it is incandescent bulbs all the way across and with all the indicators, but that's it. It's unresponsive because we have no I/O interface control boards. But let me flip the system over now, and I want to show you something kind of cool on the underside. And with the magic of editing, I have managed to flip the system over, get it onto its side, and I've already taken the screws off, so now that I can take the whole base off, and this is a piece of aluminum, by the way, and now we can see the underside of the system, which shows us the backplane, which is its own absolute nightmare, and the linear power supply right here, which has a bajillion screwed terminal blocked connectors right here, and the 4 screws that hold the power supply into the machine itself. It's actually quite easy to take out. I'll explain that one in a moment. So on the very front here are the 3 ribbon cable connections which send the logic signals up to the front panel. We also have, for the purpose of driving the lights, the power switch and various controls there, heavy wire which then runs back and comes back to the power supply. The backplane, as we can see, is a green printed circuit board, but down here on the peripheral bus side, as options are installed, there's also a fair bit of hard wiring that goes in as well. This is all wire wrap, so it's a little bit of a nightmare. And then over here on the far end, I kind of want to flip the machine onto its back here. I want to explain what's going on with the voltage rails. Now, for me to put it onto its back, 4-Phase was smart enough that the back base, or the bottom cover of the machine, is also the top cover, which is convenient for me because I don't have a top cover yet. I have to go to a metal shop and have one make it. So I'll take it off our block of wood, and I'm gonna bring it out to the middle here. And I'm going to take my block of wood and throw it away. There we go. Much better. So these are the DC voltage rails for the system, and one of them is ground. And yes, the color coding is correct on this black one here being the ground rail. So you notice how it's wired here, here, and here? I was talking to the guy who designed a good portion of the power supply, and he explained to me why the rail and all this wiring nonsense here is in the first place. And that is because in the initial design, they were having voltage drop issues. The traces on the board were simply not enough to handle the current that all of these boards on a fully loaded system were able to handle. So they added in the actual vertical standing metal rails. And unlike the ones on the boards, these are not laminated and shielded, so they can't touch each other. And what they found is that by running a wire to one end and going across, they were still having a voltage drop issue by the time they reached the other side. So they went, and it goes to both sides and then back to the power supply. And they were still having problems in the middle of the voltage rail. So you have these smaller wires here, which then go, and now they were able to balance it out enough that they weren't running into voltage dip issues. Because that 5 volts needs to be dead on in this machine. I was also clearly warned that these like to also break free, not only from storage, but just simply from use. It wasn't a well-designed product, but it worked, even though it was kind of a hack. The power supply, like I mentioned before, is a linear, so we do have a large ferro-resonant transformer and a bunch of capacitors that are hiding underneath this board here on the underside. I guess it's actually the top side in this case. And then we have this board here, which is doing our regulation, monitoring, and adjustment. There's little tiny blue and white potentiometers all over the place here, and these here are for adjusting the various voltages that the power supply generates. So I have +5 adjustment here, -22 here, -5 here, +10 over here, and 5 volt inrush limitation or limiting cutout is controlled via this one right here. And I have a couple of very large rectifier diodes, or just diodes in general, that are hanging out over on this side. We do have this terminal strip that's hanging out right here, and what's happening is that snakes around and disappears to the back of the machine. So I'm going to put the power cable there. This is a hardwired system, by the way. It's just a regular wall plug that's on this. I'm going to flip this around to the back, and I have 3 switches right here for 3 different voltages, and they mark high and low. Depending on how many boards are in the machine, the regulation on the system varies as well. You use those switches as your coarse voltage adjustment before you use your fine voltage adjustment, and it's available on the back. Also available on the back, you may be able to see them in here, you can definitely see them right here, are these red and black terminals. It is by no coincidence that if I take a multimeter from that time and I were to take the leads, they plug into those sockets. This is intentional. So the engineer I was talking to with the power supply said that he hated having to do adjustments and tweaks and testing on this so much when they were in the racks. He requested, can I have voltage test points on the back of the machine? And there they are, and every 4-phase machine has them, thanks to him. This made my life a lot easier. You know who you are. I'm sure you're watching this video, actually. Thank you very much. But what we also ran into was that the backplane has been upgraded once before on it. So with this version here, it uses a very primitive double-sided wiping slot. I'm not even sure how I explain it, but he mentioned that if the connections on the cards got dirty, the system started singing from the dirty connections. And I ran into that when I was working on this. So I thought at first that was a cap issue, so I went over, reformed it, recapped the power supply, you know, the usual thing when you run into stuff like that. No, I just had to clean the card edge connectors. And at the same time, I had to resolder some of these, but you get the idea. And lastly, I want to point out on this machine here, the actual terminal and console interface itself, which is this giant group of Winchester connectors, which sits on the underside of the terminal distribution board that I mentioned is normally sitting on top of the power supply. These Winchester plugs are a pain in the butt to get. I have none of them myself. I have Winchester connectors for the NP80 system, but that's completely unrelated and physically different sized connector. So you have your video that comes out on this here, you have your control signals from the keyboard that come back into this, and I guess you have an output that would also go for, say, a beeper, or if you have intensified, you have something like that. Again, it's difficult to find specifications on how the video signaling was supposed to work. This was for four-phase engineers to just know. It wasn't supposed to be for the general public to work on like its RS-232. So now we have gone over the entire 470 system. I've gone you through the expansion boards, I've gone you through the main system board, we've gone through the RAM. I've explained to you now already that we are missing a number of components to make this a completely functioning system. So unfortunately there doesn't seem to be, at least at the making of this video, any Centurion success stories that are going to come out of this. But I've also been rambling on long enough, I think, for this video here, but we still have a lot to cover regarding the peripherals and the expansion capabilities of this machine. Notably, like I've mentioned, the 490 CPU expansion and the NP80 expansion chassis. So I'm going to end the video here, and in our next video, we're going to talk about those. I really hope you enjoyed this, and by the way, in the next video, we're also going to talk about whatever happened to four-phase. We obviously know now that they were in great places in the 1970s. Where did they go after that? Where are their offices now? You'll actually be surprised on the answer with that one. But until next time, have a good one.